Okay, good afternoon. It's a pleasure to welcome Ashwin Vishwanath here. He received his undergraduate degree from IIT Kanpur, his PhD from Princeton, then he was a Pappalardo Fellow at MIT, moved to Berkeley as a faculty member, and in 2016, I think, moved to Harvard, where he's the Leverett Professor of Physics. And he's a well-known condensed matter theorist, received a number of honors, including this year, the Oliver Buckley Prize of the American Physical Society, and election to the National Academy of Sciences. And today's talk, he's going to tell us about the fact that quantum circuits, quantum operations that include non-unitary things, measurement and feed forward, are much more powerful than those that are just purely unitary operations. And he's going to put them to good use, creating interesting quantum states with non-Abelian defects in them. So welcome.
Hey, thank you, Steve. Always great pleasure to be here at Yale, meeting a lot of old friends. So I'm going to be telling you something that I think there are many more experts in this room and I myself am somewhat of a new entrant in this field. But what I want to do is to really use this quantum hardware to create states of matter that we are very interested in, things that we have been looking for a very long time, states which have these non-Abelian anyons. And one of the interesting twists that came out in this project is that one very efficient way of making them, in fact, we had to get this efficient to actually achieve this in an experiment, was to use measurements. And this is really something that we learn about in the quantum mechanics courses, and then we promptly forget about it because we don't actually use it when we use quantum mechanics, at least kind of quantum mechanics that I and many other condensed matter people do. Okay, so that was really a very exciting thing for me to actually see measurements at work, not just as this thing that kind of confuses us, but actually, is put to work to do something that we otherwise could not do that efficiently. Okay, but the real hero of the story will be the anyons, the non-Abelian anyons. So I'm going to start by telling you a little bit about non-Abelian anyons, reviewing all of that physics, and about the states, the underlying medium, which allows you to create these as excitations on top of them. Okay, these topologically ordered phases that really form the backdrop for these anyons. Okay, so this is kind of the important slide. We had these amazing collaborators. Unfortunately, all of them have left Howard now. Nat is a postdoc at Caltech, soon to be faculty member at Stony Brook. Ruben has moved already to Chicago as a faculty member, and Brian has moved to UCLA as junior faculty. And these were our wonderful collaborators at Quantinium. This is the experiment I'll talk about, and it was funded by this Simons Foundation grant, collaboration grant that basically allowed us to do whatever we like. We had a title that encompasses everything that we are interested in. Okay, so you've all heard of bosons, fermions, the distinction between different kinds of identical particles. And this really has to do with the exchange of particles, right? You have particles, this is time, they undergo these trajectories, or you could exchange these identical particles. And the boson versus fermion, as you all know, is whether you get a plus or minus sign for these exchanges. But there is an additional possibility, you might think, what if this exchange allowed for a phase factor of something in general that went between these two? And that would, of course, have some dramatic consequences. So for instance, instead of exchange, you can actually get the particles to return to their original position. So this is something, a braiding of one particle around another. And if you have this general phase, unlike these two limits, this trajectory would actually remember that it went around the other particle and record that with a particular phase of e to the 2i theta.
Why do you say the double exchange is a braiding? Why didn't you say that for the single exchange?
If you like, I will call the single exchange braiding. Also, I'm not going to be very, what do you call it? Very, yeah, I don't have a strong opinion. Sorry? So this is also a braid? You want to? Okay. So that is also a braid. Question behind. So, yeah.
Should I think of this as space-time?
Yeah, think of it as space-time.
There's how many dimensions?
Very good question. Yes. So, so anyway, this is really particles remembering their past, and this is intrinsically quantum. And the third point I want to make is this is really specific to two spatial dimensions. Okay, so example, in 3 dimensions, doing this kind of double exchange, you can sort of undo it. Topologically, if these things are very far apart, you can undo it, which goes back to our original result that there are just bosons and fermions. Okay, but in 2 spatial dimensions, you're allowed this extra degree of freedom, which allows you to get these anyons. Yeah, so theoretically, these things were proposed a very long time back as a possibility in 2 dimensions. And another way to see why 2 dimensions is special, actually, you could imagine a way to cook up this particular phase. Okay, and one way to do that is to go back to the Aharonov-Bohm effect. You have charged particles that are encircling a magnetic flux. They pick up a phase. And this phase, if you imagine that your particles were somehow attached to these fluxes, they could move around carrying these fluxes with them, then you would get this, the phase that you wanted when a pair of particles are exchanged or taken around one another. Okay, so, so how do you get that? You can see again that if you want this situation to occur, you want to be in 2 spatial dimensions where the flux and the charge are essentially both point particles, okay? And how do you do that in nature? Well, there's one big gift we have, the fractional quantum Hall effect, where these are naturally associated with one another. I'll come back to that in a second. Another is a situation where you have an emergent gauge theory. So you have a system where the excitations look like charges and fluxes, and then you can have particles that, you know, these are the particles in your theory, or they're composites, which will allow you to get these anyon statistics. So these are 2 ways in which we can hope to achieve them in nature. And the first, the anyons are really the excitations in the fractional quantum Hall effect. So I was looking for a figure for this, and I found this poster conveniently outside. So this was awarded the Nobel Prize in Physics. And for example, the 1/3 Laughlin state over here, this is sort of a picture you'll often find on the web. You see these kind of flux tubes piercing these charges. So this is thought to be, you should think of them as vortices of the electronic fluid. And again, you have the situation where you have a flux and charge composite. And these excitations were very early on by Bert Halperin and others realized to carry the fractional statistics, the anyon statistics. And more recently, there's been a measurement of these, the statistics, more directly in experiment. Okay, so that is one way to achieve this. Another way, actually, which occurs in model systems so far, is these so-called toric code model. So this is a model entirely made of spins, but you give a certain kind of energetic so that the ground state of the system or the low energy state can be viewed as a quantum coherent soup of closed loops. Okay, now what are the closed loops? The loops are going to be built up of more obvious kind of degrees of freedom, just the spins over here. So for example, this is a spin up or spin down, and you can see that I've taken a configuration where these orange spins, the down spins, form a closed loop. And you can do this by endowing this with certain kind of energetics. So for example, if I think of up and down spin as being measured by these Pauli operators, these sigma z's, having this term in the Hamiltonian will encourage having closed loops. Okay, and that's how these loops emerge. Then you have another term that gives you quantum superpositions of these closed loop configurations. Okay, so product of these sigma z's requires even number of the sigma z's to be, let's say, -1. And therefore, the even number really means that you have these closed orange loops. Okay, and this term commutes with this one, so it does not violate this closed loop condition, but it gives you quantum fluctuations, the product of sigma x, inserts these loops. And there's an analogy with gauge theories. This is really like the Gauss law, sort of a binary version of this divergence of the electric field being zero. Here, the divergence, the plus or minus, is either 0 or 1, and you constrain it to be 0, have just closed loops. And this is sort of like the magnetic field squared term that gives you some quantum dynamics of the electric fields. Okay, so this is really a way trying to simulate a gauge theory described in terms of electric field, closed loops of the electric field, and the ground state of the system is really an equal superposition of all of these closed loops. Okay, so what has this got to do with the anyons? Well, this is sort of the background, the stage on which the anyons can exist. And if you think about this superposition wave function, you can make an excited state where you decide to break this constraint and actually have an endpoint. These endpoints are like charges. They're sources of these electric fields. And they are really going to be our Abelian anyons. Okay, our anyons. The endpoints over here will give us charges. There is sort of a dual set of excitations which correspond to flux. You put those two together, you get another excitation. This is another way in which we get excitations that are ultimately like the anyons that I was talking about. Okay, so really these are our two routes to realizing these anyons. I've used a qualifier over here that will become clear in a second. One is in terms of these emergent gauge fields and models like the one I showed, charge and flux, and then you can also get bound states of the two. So I call them E and M, that's the flux, and the bound state is referred to as F. It turns out, although these are bosonic, this bound state turns out to be a fermion, at least in the story code model. And then we had the fractional quantum Hall effect. This is another example of that, where you take electrons in a strong magnetic field, put them at just the right density, and you end up getting these fractions. Fractions are really revealed in a measurement called the Hall conductance. And they're precisely quantized. For example, the 1/3 over here refers to the kind of state that I was talking about before, the Laughlin state. Okay, so you can notice the magnetic field over here is fairly large, 12 Tesla. Previous thing I showed you was even larger. Huge development more recently is people have been able to realize the same state of matter, but without applying any magnetic field. Okay, so you can switch off. This has been sort of one of the demanding aspects of these experiments. You needed very clean samples. You needed large magnetic fields. It turns out a lot of this can be replaced by these two-dimensional materials that are appropriately twisted against one another. Okay, and the twist gives rise to energy bands that, after some spontaneous breaking of symmetry to get a ferromagnet, for example, ends up giving you this nuclear 2/3 state, the one over here, but it's actually realized in zero magnetic field. Okay, so anyons are really, coming into the lab and with much less restrictive conditions, and that has been a very exciting thing over the past few years. Okay, now there's a further generalization of this physics, the non-Abelian anyons. And again, you can motivate them in terms of the Arnaud-Bohm effect. So that is sort of the toy model on which you can base a generalization that will allow you to get to these non-Abelian states. And imagine instead of just having a charged particle, this is a particle with some internal degree of freedom. Okay, and let's call it color just suggestively, because in fact, the non-Abelian over here is closely related to the non-Abelian of the Yang-Mills theories. These color labels, instead of just acquiring a phase when you go around the solenoid, you could do something a little more interesting to your particle. You could rotate it with the unitary matrix that rotates you within this color space. And this would constitute a non-Abelian generalization of the Arnaud-Bohm effect. Okay, and you can go one step further. You can imagine a situation where you have charges like this one, and you have this flux, and they're all dynamical. They're all created out of this medium. You can also have composites of them. And that is really intuitively what we are thinking about when we talk about non-abelian topological order. Okay, so to contrast the two, the abelian topological orders are, you get this phase. The non-abelian ones, if you do a similar, take one particle around another, it turns out just having these particles in the ground state gives rise to a certain degeneracy of the wave functions. Okay, there's more than one candidate ground state. There's more than one state in which they can be in. And this process over here ends up giving you a unitary matrix that is applied on these degenerate states. Okay, so that's one of the defining features, generalizing the phase to a unitary matrix. There's another aspect that is different from abelian anyons. So we said in the abelian case, if you put together a charge and a flux, you can get a fermion. You get a single outcome. You get a third particle. In the non-abelian case, it turns out there are at least a pair of particles. You fuse them together. You bring them close and fuse them so that they form a single particle. Well, there's more than one outcome when you do that. Okay, so this is the non-trivial fusion of these non-abelian excitations. This is an example for one of the simplest kinds of non-abelian theories. This is a slightly more involved fusion channel where a pair of particles fuse either back to the vacuum, they just disappear, or they reappear as this non-trivial particle. Okay, this is called the Fibonacci anyons. Because you think about it, this will give you a growth of the number of degenerate states similar to the Fibonacci sequence. Okay, as you have more and more of these excitations. Okay, and again, they're related to Chern-Simons gauge theories. They're related to gauge theories with some non-abelian gauge group, okay, roughly speaking. Again, there's a lot of very seminal work but done by Nick on these kind of theories. Okay, we'll get back to that. So how do you realize anyons? Other realizations of these anyons. Well, we talked about how just by having a twist, you can realize these abelian quantum Hall states. And this really goes back to how much control we have over our quantum systems versus maybe the scale at which they are realized. Okay, so this is somehow the sweet spot. This is really the length scale, tens of nanometers, where people can create these twisted materials, or even the quantum Hall effect actually is roughly in this scale, in this regime. You have a reasonable amount of control. For example, you can change the density of electrons. Okay, you can vary it with a potential, and that filling control actually gives you a lot of, is very convenient when you're in this length scale. Okay, now you could go, to the, trying to get more control, or you could go in the opposite direction, really go down to the angstrom, the lattice scale. And this is, just the regime of quantum solids. This is really a place where many of us hoped we can see anyons. Okay, and there are proposals for things called quantum spin liquids, which will simply be anyons in a material, this sort of quasi two-dimensional material. So far, there's no clear-cut realization over there, but this is ultimately where we'd really like to go. You could get entirely new materials properties if the constituents of your system are actually these exotic particles. But for now, we'll content ourselves sort of going in the opposite direction, going to larger length scales. So effectively, this will be fewer degrees of freedom, but we're going to benefit by having much more control. And that is really going to these quantum platforms, things like the superconducting quantum bits that you have here at Yale, or these neutral atoms, trapped in tweezers. It's another very exciting platform. Our own favorite for these experiments are going to be these trapped ion systems, where we can actually do this procedure of measurement and feed forward. And this is where we're really going to talk about trying to create these non-abelian states using these measurement protocols that I'll talk about. Okay, so this is going to be a somewhat different way trying to create these states of matter than you're used to. The way we usually think of creating states of matter, you have something that is macroscopically large. You have Avogadro number or, many billions of these electrons in a quantum Hall system, for example. And your job as the experimentalist is to find the right conditions and simply cool it down. And when you do that, it will self-organize into this interesting quantum state, and the excitations will be these anyons and so on if you're lucky. But here, what we want to do is something that is a lot more active. What we're going to do is we're going to begin with these, with some bunch of quantum bits down here. All the quantum bits are independent of one another. If you like, you go and measure them all, make sure they're all sitting in the 0 state in one particular state of the quantum bits. And then through a very controlled process, for example, using these quantum gates, take pairs of these quantum bits and entangle them, get them to interact and entangle them. Using this procedure, we want to create a quantum state up here at the end of this circuit, which will then have excitations which correspond to these anyons. Okay, it's a different way of trying to create states, and this is only allowed if you have exquisite control over the quantum bits. Okay, so really the question maybe we want to grapple with before we get to that is, why would you want to create non-Abelian anyons? Okay, of course, this is a new and new state of matter, and a new kind of excitations. But there's been a big push in this direction, because people notice that this idea of creating a pair of these particles and taking one around the other, those kind of processes will affect a unitary operation on your states. This is exactly what you want to do if you want to create a quantum computer, right? You want to be able to implement unitary operations. And the advantage here is because of the topological nature of this physics, the fact that this degeneracy of the state, the states that you get, are really contained in two very well separated excitations. There is some inherent robustness that gets around the main problem of quantum computing, which is decoherence. Yeah, Shankar's question.
How many dimensions should I associate with your circuit in the previous slide?
That could be in any. Yeah. So the question is, how many dimensions this circuit over here is shown in one dimension, but there's a very similar thing that you can draw in 2D, for example, where these bricks over here, maybe in one time slice they're all horizontal. In the next time slice they rotated 90 degrees, and then they entangle qubits in the orthogonal direction. Yeah, there is. I should maybe have stolen a more 3D version of this from the web, but yeah, you can easily do it in any number of dimensions. Usually the layout that people have is 1D or 2D. And I'll talk a little bit about the layout for this quantinium thing. It's kind of interesting because the layout is really determined by the gates, and we'll come back to that. Any other questions? Oops. Okay, the other thing that we found along the course of this project is that there are many amazing properties of non-Abelian topological phases, or if you like, non-Abelian anyons. They're about as the complexity that you get going from Abelian to non-Abelian, I would now say, is about the same as going from a trivial state to the ones with Abelian anyons. Okay, so there's really many interesting new things that appear, and just investigating them, if you have a concrete platform, something that actually realizes them, would be amazing. The third thing is, it's really hard to create these states. Okay, we got really lucky with the fractional quantum Hall effect and realizing the Abelian anyons. Even before people actually knew they were Abelian anyons, you had this phase of matter discovered. There are actually, it turns out, some very nice candidates for the non-Abelian states in the fractional quantum Hall effect. So the best candidate right now is in the 5/2 and 7/2 fractions. These are the only even denominator fractions that people regularly see. And there was a state proposed by Nick and Greg Moore, probably here at Yale, I'm guessing. And amazingly, this is the best candidate right now for these fractional quantum Hall states. Okay, and I think there's still the smoking gun evidence has not come in yet. But I think if most of us were to put money on it, we would actually put money on Pfaffian or a close cousin of that, the anti-Pfaffian being realized in these fractions. Okay, so there's also another candidate at 12/5 and 17/5. Again, another proposal due to Nick and Rizai. Again, quite fairly compelling evidence from numerics, but the experimental evidence is not quite in yet. They're even more delicate fractions. Okay, so we have some nice candidates in the fractional quantum Hall, but they're more delicate than the abelian ones. And it would be great to have other ways of realizing these states. Okay, so so this is the state that I'm going to describe a construction of. We won't need many details of this, but just to make sure it's not a black box, we are going to create a non-abelian topological phase. And the simplification over here is that we're going to associate this non-abelian phase with a group. Okay, so not all of these non-abelian phases or even the abelian anyons are naturally associated with a group. But there's a subset of them that are easy to describe because they refer to things that we know well in group theory. Okay, so the analogy that you should keep in mind is that we talked about the toric code, the simplest model where you had this kind of a soup of these loops. You could think of it as a gauge theory. And the group that enters that gauge theory is really the simplest group you can have, the Z2 group, okay, even and odd. And there we had the endpoints of these lines. There were charges. You can think of them as Z2 charges under Z2, representations of Z2. There's a dual excitation, the flux. That's what you get the Berry's phase on going around, the Arnaud-Bohm phase on going around. It's a flux of 0 or pi. And then there's a dion, the product of these two, which, as I said, the nice thing about that comes out is that it's a fermion. Okay, so people try to simulate these in quantum computers as well, the simple toric code, because there's a way to get at a fermion. If you're trying to simulate electrons in a molecule, if that's what you want to compute, it's not that natural to put it in a quantum computer where everything is bosonic. Okay, you want to have something fermionic to represent the electrons in that molecule. And one convenient thing to do, it turns out, rather than trying to have a Jordan-Wigner string to implement the fermionic character, is to actually go and create a toric code. Use the fermions over there to encode the fermionic nature of the electrons. Okay, so if you look at the encodings people have, efficient encodings of fermionic statistics, so you look carefully, it's really just the toric code sitting inside. So the people have been interested in creating these states on quantum computers. And another way to think about it for the particle physicists is that you can imagine starting with the continuous, a Lie group, a U1 gauge theory like Maxwell electromagnetism, and then condensing a charge 2 Higgs field. Okay, sort of like a superconductor. You condense some particle, and then you gap out the photons. It's a completely gapped phase. But if you didn't condense the fundamental charge, you have a remnant of the charge, which is just C2 valued. It's kind of like the quasi-particle in the superconductor. And you also have the vortex, the flux, and then you could have the bound state of the two. Okay, so now what we want to think about is a non-abelian generalization of this. Okay, so imagine you start not with Maxwell's theory, but a Yang-Mills theory, SO3, let's say, based on the SO3 group. And then you Higgs it down with some higher representation of SO3, higher spin representation, so that there is still some life left in this Higgs condensate. Okay, it's gapped, but there's some life left. And what we want to break it down to is a subgroup of the rotation group, D4. These are really the symmetries of a square. So if you have a square living in 3 dimensions, it has rotations, 90-degree rotations around and the multiples around the vertical. And then you can have 180-degree rotations around in the plane. The axis is in the plane. That generates the group D4. It's got 8 elements. And again, you can think of the magnetic excitation of this when you gauge the symmetry group. These are really the not quite the group elements, but the conjugacy classes of the group elements. All the group elements that look like each other are grouped into these conjugacy classes. And there are 4 different conjugacy classes. Over here, they are like the magnetic fluxes. Okay, and the charges are simply the irreps of this non-abelian group, irreducible representations. 3 of them are just one-dimensional. They're like But then there is a two-dimensional irreducible representation, two-component object, on which you can represent the action of this group. Okay, so there's an amazing fact that the number of irreps is the same as the number of conjugacy classes for any of these finite groups, despite the fact that there's no one-to-one correspondence between them. Okay, so there's some sort of electric magnetic correspondence, and then you can have the combinations of these. Okay, and we won't really need this, but it's not simply a product. You have to do something a little more complicated. All in all, you get a complicated looking theory, which has got 22 of these excitations, 21 non-trivial ones, and then the vacuum. Okay, but we won't have to engage with all of them. Just remember this number 22 is going to appear again later in this talk. Okay, so we want to create this non-Abelian phase. Okay, on the face of this looks like a really complicated thing to try to do. Why start here? But from a different angle, it turns out this is the simplest non-Abelian phase you can create. And maybe I'll come back to that later. Okay, so let's go to the second part, which is really trying to create this state, and this is where the measurement stuff is going to come in. But before that, any quick questions on the introductory part?
Right, the convection relation between the particles. What about dynamics? Is there any expectation?
Not much, yeah. So this is a state of matter where everything is gapped. So of course, if you look at energies below the gap, it's just the vacuum. Okay. The thing that gives it some life is we're going to go and look at excitations on top of the ground state. Okay. So we're going to create these excitations, and it's going to be very much like the toric code that when you create them, they're going to sit around, they don't move around. But you can use unitary gates. That's what we're going to do. We're going to use to move them around, yeah. And essentially, it's going to be an adiabatic motion of these things. And we're going to test, whether they have the kind of non-Abelian statistics that they're supposed to have. Okay, so now let's switch topics to measurements. So the interesting thing that I need to highlight is that measurement can be used to create interesting quantum states. I'll use the word entanglement over here, but essentially you can actually create interesting quantum states, which sounds completely backwards, right? Because when you go and measure a state, you actually collapse it, and that should just be a vegetable, it's just what you read out. Okay, but the whole idea is going to be that we're not going to measure all the qubits. We're only going to measure a subset of the qubits, an ancilla qubits, if you like, and the rest of the qubits are going to be doing something interesting. Okay, so here's an example. So this is an example of a very trivial product state. 2 qubits, both are up. This is sort of the most interesting state that you can get with 2 qubits, the Bell state, both up plus both down. Okay, this is maximally entangled. This is the stuff that Alice and Bob share in this quantum teleportation protocol and all of that. This is maximally entangled, and you can think of it as the maximal superposition with the constraint that the product of sigma z is 1. Okay, if you take sigma z as being the Pauli operator +1 for spin up and -1 for spin down, if I tell you sigma z, the product is 1, and I tell you give me states that satisfy this constraint, you could have picked both up and both down, but if you want the maximally entangled one, that's the one where you combine both of them together. Okay, and then here's another state. It looks complicated in this particular basis, but actually it's not entangled because you can write them as, the plus state, the spin along the x direction independently on for the 2 qubits, okay, or for the 2 spins. So this is a not entangled state. But imagine you start with this and go and measure the qubits. Don't measure them individually, but go and measure just the product sigma z, sigma z. Okay, and I can tell you how to do that in a second. But let's say you go and do that, starting with the state. Well, this is these 4 branches over here. And if your measurement outcome is +1, so let's say you go and measure and you find the measurement outcome +1, it certainly couldn't have been either one of these branches, so they're gone from the wave function. But it could have been this or it could have been that, and you have no information to distinguish the two. Okay, so if you were to make a measurement of this product alone, and not the individual quantum spins, you find +1, you actually end up creating the state. Okay, so this is a way to create an entangled state using measurements. And the whole talk will be just kind of repeating this on more and more complicated states to get the thing that we want. Okay, now, of course, you can ask, what if I got the measurement outcome -1 rather than +1? Okay, so one thing you could do is throw it away, which is fine if you just have 2 qubits. But we're going to have a very large number of qubits, and the wastage will go up exponentially if you're really finicky about what measurement outcome we want. It's called the post-selection problem. So it's very important that you don't rely on post-selection. You have a way to fix the problem if you end up getting -1. And so if you do get -1, what you do is you fix it. So let's say the measurement outcome M is either 0 if it's the right one, or 1 if it is the wrong outcome. If this product is -1, you simply go and apply a unitary operator at the end of this process. You go and flip the first spin. I could have flipped the second one also, but let's say if I flip the first one. So in case you end up getting this pair over here, measurement outcome is -1, you go and flip the first spin, you'll end up getting back to the state that you wanted. Okay, so this is a measurement-based protocol where the measurement is outcome is random, but the final state you get is deterministic. Okay, you select the unitary you apply depending on the measurement outcome. Okay, so this is called measurement and feed forward. If you have this capability, you can use measurement to create a target state. Okay, so hopefully that simple example is clear. Okay, so how does this help us? Okay, so there is a very simple example where you can show that it helps us, which is imagine trying to create the simplest kind of topological phase I talked about, the toric code. And so this is supposed to be a 2-dimensional system, but I'm drawing it as 1-dimensional. You start with all of the quantum bits being unentangled, so all the product state. Let's say all of the spins are along the x direction. And then you ask, how many gates do you need in order to create the toric code ground state? Okay, now, actually, the number of gates is not such a useful concept. Actually, what is more useful is how many layers of these gates do I need? So basically, gates that do not commute with one another, or gates that are taking something in common, some qubit in common. These have to be applied in separate layers. You can ask how many layers I need. And it turns out this depth is actually linear in the system size. The number of gates you need to apply that take qubits that are near each other and end up giving you this entangled phase, this non-trivial phase. The depth will scale with the linear size of your system. Okay, so as you get to larger and larger number of qubits, you're asking more and more of your quantum computer, where typically what you're limited by is how long these things take coherent. How many layers of these gates you can apply. Yeah.
The Albert 21 does not have D6H symmetry. D6H, this seems to be broken. You should decide on one side smaller, shorter than the other.
Oh, yeah, you're saying over here the stabilize. Okay, so the question is, why do these? So what is shown over here are
The Albert
yes, it does not have which symmetry? Sorry.
D6H, which is the symmetry on the X side.
Okay. So this is one. Okay, so the question is, why is this snapshot over here not respecting the symmetry of the underlying hexagons? So this is one snapshot of the quantum wave function. So if you were to actually take the quantum state, which is a linear superposition of many of these different configurations, that state will have a C6 symmetry. But if you take any one snapshot, it appears to break the symmetry. Now, if you look at a physical quantity, like what is the dense, some physical quantity that might measure the breaking of symmetry, and you go and average it over all of these many snapshots, it'll end up being 0. Yeah, but both of these were essentially trying to do this sort of unitary preparation. And they succeeded in the sense that these numbers over here tell you how low the energy of the state is and measured for the stabilizer Hamiltonian. If all of them were +1, this would actually be the ground state. They all succeeded, but they pay the cost of having this rather deep circuit. Going to bigger system sizes is going to be challenging. Okay, now it turns out that if you allow yourself measurement, I'll describe how in a second. if you allow yourself measurement and this option of being able to correct your state based on the measurement outcome, you can actually create this in a constant depth, regardless of the system size, the depth of the quantum circuit, and how many measurements you need to make is going to be independent of the linear size of the system. And this is actually, we did this with the Quantinium for the toric code. And these are the stabilizer values you get using this quick method. And it compares very well, actually, with this unitary depth. In fact, I think it's a little better, showing that it works. Okay, so what is actually the protocol? So the protocol over here is going to use this trick I talked about before, using measurements to create states, create entanglement. Okay, so let me just explain how this works for the toric code. Very quickly, because this is really what we're going to, we're going to put this on steroids to make the D4, right? The same process. So what you really want is that these products, they're called stabilizers, you want them to be +1. Then if they're all +1, you have the toric code. Okay, so what you do is you start with a state that automatically enforces, this, let's say this product of Z's is +1. For example, you can start with all of the spins being up. Okay, and then your job now is to make sure that these B's also take on the values +1. Okay, so what you go and do is go and measure them. You go and measure not the individual spins, but these stabilizers. If you're really lucky, you'll find all of them to be +1 and you're done. The state you got at the end of it is the toric code ground state, but it's extremely unlikely. What's more likely is half of them will have the wrong sign. Okay, and half of them having the wrong sign really means that you have these endpoints. Maybe I'm flipping the terminology, but you have these endpoints where there are anyons that are simply sitting in the ground state of your system, sitting in the state of your system. And just like in the case with the 2 qubits, we need to do a cleanup step. Okay, you need to do something in order to get rid of these anyons. And actually, it turns out it's very easy to clean up. I'll describe how it is, and you end up getting the toric code topological order, the toric code state. Okay, so the way in which you go and clean up this thing is, say, for example, you got 2 of these anyons sitting at these 2 points over here. These are the wrong values of the stabilizers. You just pick a path, connecting them, and apply a single layer of gates. All of them are Pauli X. And then you can flip these endpoints, and you end up getting the toric code, the pristine toric code state. You can do this for every pair of anyons in your system. You're actually guaranteed to get an even number of them. You can do that for every pair. And in a single layer, you can end up healing the state and going back to the state you want.
Does it matter what path you take between them?
Yeah, so that's a very good question. It turns out it does not matter. Or if you like, there's a canonical choice. You can pick some central site and drag all the anyons to that site if you like. Of course, you may want to be efficient. So you may want to be not just worry about the depth. You may actually want to worry about gate count. How many X's do I apply? And then things get, the classical optimization problem can get harder, and it can make a big difference. What decoder you have. They're called decoders, how to go back from these defects to the strings. But we are not going to be worried about that type of efficiency. We're only going to care about how many layers. And all of this correction can be done in a single layer of application of X. So this is really a protocol that has finite depth as far as the unitary operations are concerned. In fact, I didn't even reveal the unitary operations. I just said, let's say you make a measurement of 4 of these sites. What people actually do is they have another quantum bit that allows them to make an efficient measurement of the 4 at once. You do some quantum gates to entangle that new qubit with the original ones, and then you go and measure the new qubit. But even including all of that, you only have a finite depth in order to create this, create the state. So here, all the heavy lifting is actually done by a classical computer. The hard part in this is you need to get information from the entire system. So you need like communication, classical communication. And then you've got to figure out an algorithm, where do I go and apply my X operators? And if you really think about it, there is actually something that is linear in the system size going on over here. For example, to communicate which parts of which stabilizers are the wrong value, you have to communicate over a distance of order the linear size. So if you worry about the finite speed of light, ultimately this thing is also scaling linearly with system size. Okay, but for every practical application, that is not, okay, I shouldn't say every practical application, but normally we think of that not being the cost. And the hard part of this being really the quantum gates and applying and doing measurements. Okay, so from that point of view, this is linear depth versus the previous protocols, which were actually these deep circuits. Okay, so this may suggest that we have a very efficient way of creating non-abelian anyons as well. Okay, let's go and apply this exact same procedure. Let's go and start with some product state, go and measure non-abelian stabilizers, if you like, or non-abelian projectors, and then simply clean it up and get the non-abelian phase where we can have these anyons. It turns out this does not work, essentially because it's very hard to clean up non-abelian anyons. Okay, they have these degrees of freedom that if you simply try to collapse them, they don't actually cooperate the way abelian anyons do. Okay, so it turns out this step is complex. It's also linear depth, if you like. So, and given that the separation between anyons is typically half the system size, that goes back to being a linear depth protocol. Okay, so the most naive way of creating this does not work. This is where we figured out a workaround, at least for some of these non-abelian phases. Okay, so that's what I'm going to tell you about. And I'll tell you that with reference to a particular model. So this may get a little bit hairy, but ultimately I'll show you an experiment that works out this model. So the details are not very important for those who want to ignore them. So what we did first is we think about a model which has 3 copies of the toric code. Okay, so you may wonder why we take 3 of these copies. We'll see very soon that that can be combined into this non-abelian phase. Okay, so the 3 copies correspond to 3 different colors of these spins over here. And you can define these stabilizers on this bigger model. And these stabilizers, if you implement them for each of the colors, they're going to end up giving you a toric code. Okay, so I didn't spell out what they are. Essentially, it's something on like a Star of David over here, the green Star of David over here. You have product of the X stabilizers. And then on the triangles, like the green triangles over here, you have product of Z's. Okay, very similar to the toric code we had before. They now come in 3 colors. Okay, so if you do use these stabilizers over here, you end up getting, so here they're shown. If you use these stabilizers, you end up getting a wave function. So we said these wave functions can be thought of as loops, closed loop configurations. You have these closed loops. The only thing now is that they have 3 colors. Okay. And correspondingly, there are 3 kinds of anyons, E anyons and M anyons. Everything is abelian. You take pairs of them and fuse them. You get a unique fusion channel. Okay, so what is the twist? We have to add a twist over here to get something non-abelian. And it turns out the twist is extremely simple. In fact, it's hard to see why this does the job for you. All you have to do is take the uniform amplitude of superposition you had before, keep the amplitude, but change the phase. You can change the phase in a very particular way. When you see a collision like this, 2 electric field lines of red and green encircled by the blue, you're going to modify the wave function, not the amplitude, but not the magnitude, but just the phase, just switch the phase around, make it -1. And from our knowledge of various things, including topological phases of matter, topological insulators, whatnot, over many years, we have come to understand that this procedure will convert this very innocuous toric code, 3 copies of toric code, to something non-abelian. In fact, it will convert it to precisely this group, this D4 gauge group that I talked about. You can again label the particles in terms of electric and magnetic particles. These are abelian, but it turns out these magnetic fluxes are actually non-abelian. You fuse them, they create a shower of these particles, which are, they can create these other particles. So this actually represents a non-abelian phase. Okay, so our goal will be to create this particular wave function first, and then look at the excitations on top of that. In particular, we want to create these M excitations and show that they are non-abelian.
Did you show the parent?
This is the parent Hamiltonian, yes. So it's very similar to what I had before. So the B's are still the same, product of Z's for each color. but the A has been modified to give you the appropriate change in sign. Okay, and all you do is still you take a product of X on the Star of David, but now you address it with some additional gates over here, Control Z on the inner hexagon. That's the only change that you make. Again, what you can show is that these are again stabilizers in the sense, for example, you square these operators, is square to 1. And they commute with each other. The B's commute with themselves, but it turns out in general, these A's don't commute with one another. Okay, so there's not a commuting stabilized Hamiltonian, which turns out to be important in order to get the non-Abelian extensions. Okay, but that's a side remark. If you are in the limit, if you're in the sector where all the B's are 1, then everything commutes. Okay, and that's the sector we're going to be in. Okay, we're going to create it in that particular sector. And the way you do it is, again, you're going to start with all of the spins in along the Z direction. B is already set to the value you want. And you use measurement to go and fix the value of A to get the right value. When you do that, you get the ground state. That's the state you want. Okay, so instead of showing you how to do that in detail, I'll just show you the experiment because that will serve the dual purpose of showing you the implementation. Actually, how much time do I have, Steve, just to? Okay, so I'll show you the experimental implementation very quickly. Okay, so this is really the idea will be to try to pack all of this into a limited size. You have a limited number of qubits. And we'll try to show some special features of non-Abelians. If I don't get to it, these are two things I found quite amazing that I didn't quite know before. I didn't know it in this language. It's actually possible to have a single anion on the torus when you have a non-Abelian theory. Always think of them as coming in pairs. This is possible in a non-Abelian theory. Not on the sphere, but on the torus. There's also this way of linking world lines of these non-Abelians together so that no two of them are linked, but all three together form a form this Borromean link. And you expect for these non-Abelians to get a minus sign. And this is something that we could check in the experiment. Okay, so this is the quantum device we worked with. Trapped ions, so I won't go into the details over here, except they have very good fidelities for 2-qubit gates. They could do this mid-circuit measurement and conditional logic. Okay, so these qubits are kept along a racetrack. And when you want to entangle pairs of them, you bring them into this region over here. And then you shoot some laser pulses to get the gates you want or to measure them. Okay, and then you take them back and store them in these rings. So although this looks one-dimensional, the entanglement is not one-dimensional. It's whatever you choose it to be. And when you store it, they don't talk to each other anymore. Okay, so you can, for example, create a torus simply by culling the qubits according to a certain protocol and entangling them. Okay, in fact, we use that torus geometry to get better finite size kind of effects. Okay, the all-to-all connectivity was helpful for us, but not very crucial. What is really important was the measurement. Okay, so I have some slides showing you how this works, but I'll kind of skip through this, except that they can do all of these. This is how they do the gates, how they move these qubits around. And the very important thing is that they move them. They can also do this thing where they skip over the neighbor. So they're not constrained by the one-dimensional geometry. You can pick any 2 qubits and entangle them. Okay, that's kind of the. Okay, so this is what we ended up doing. So we have these gates that entangle the quantum bits. We have 27 quantum bits, and we had some extra ancillas in order to do these measurements. We go and do certain entangling gates. This is a very important gate. It's a control ZZZ, related to a control ZZZ gate. This is the non-Clifford gate. You really need that in order to make something non-Abelian. And then you go and measure, and then there's a cleanup step where you are able to fix the stabilizers and get the right, and get the ground state. Okay? And you can go and measure the value of these different stabilizers at the end of this protocol. The nice thing about this protocol is that when you get a defect, the only anions that you excite are actually the abelian ones, not the non-Abelian. So then it's very easy to get rid of, to clean them up in this short string, this kind of protocol to clean up the thing. Okay, so I'll just flash the size. the measured stabilizers. And the important thing to note is all of them are pretty close to +1. Okay, and this tells you you've gotten very close to the ground state. You can set a bound on the overlap with the actual ground state. So it's pretty high fidelity per per site of this 27 qubit lattice. Okay, now of course this is a system that you don't really need a quantum computer to solve. You don't even need a classical computer to solve it. You can solve it with pencil and paper, right? All of those stabilizers commute. So, but the advantage of doing this on a quantum computer is the quantum spins, the state that you create actually represents this non-Abelian topological order. Okay, and then you can do further experiments on it. For instance, you can try to check the non-Abelian nature of these excitations. So you can create a pair of these non-Abelian excitations. And if you fuse them back, they just go back to the vacuum. They just create it on the vacuum. But if you take a pair and another pair and you take one around the other and then fuse them, then they are, depending on the channel, they don't go back to the vacuum. They can create another excitation. And you can check if the other excitation is created by going and measuring the stabilizers. The stabilizer should have the wrong value at the end of this process. And that's essentially what we do over here. These strings, creating the non-Abelian excitations, they correspond to some unitary operators like some product of X and then some additional stuff. I won't go through this in detail, except to show you that at the very end, we end up with these two hexagons lit up, which really means that there are some anyons that are created at the end of this braiding process, showing that it's non-Abelian, has non-Abelian statistics. Okay, there's another interesting thing that maybe I'll come back to the end of the questions. You can create all of these ground states. So we remember we had 21 non-trivial excitations, 22 in all, including the vacuum. Each of them corresponds to a ground state on this torus, and you can create all of them. But there are some that you might have thought would have been ground states based on the analogy with the toric code. But it turns out that they're not. They're actually excited states. That's why they're not part of this count. And actually, if you go and look at the stabilizers for those states, and of course, some of the stabilizers are now going to have the wrong value. That's why they're not the ground state. And if you're going to ask how many of them have the wrong value, it turns out there's just one that has the wrong value, which tells you that there's a single anion on the torus. Okay, and this is something actually we knew, for example, even for these Ising anions, P plus IP on the torus. We all actually, we didn't have this language, but it's very clear over here because of this, these stabilizers. Okay, and finally, we did this Borromean braiding. So these non-Abelians are really good at detecting different kinds of knots. Okay, so Abelian anions can only detect this kind of linking. If they link, then they know it because of the mutual Arnaud-Bohm phase. But you can have this configuration over here. It's slightly deformed so you can see it over here. If I cut this blue loop over here, I can slide the red out of the green. Okay, so no two of these things are really linked together. But all together, you cannot slide them off. So it's really a property of all three of them. Okay, and for this particular topological order, if this is the space-time diagram of pairs of these M particles, blue, which are green, blue, and red, we expect that at the end of this process, you start from the vacuum, you go back to the vacuum, but you get a minus sign. Okay, so this could never happen for Abelian anions. They could never detect that you send them through this particular braid. Yeah, and this is something that you can do. This is actually the hardest experiment they did. You have a qubit and controlled, depending on the what state the qubit is in, you either do this Borromean braid or you do something that's very close to it but is not braided. And then you can compare the relative phase between the two paths at the end of it by standard interference experiment on the qubit you controlled on. And they get a value that's pretty close to the one that's expected from the theory. Okay, so this is also something that you can confirm. And I think I'm out of time, so let me end with my conclusions. So on this 27 quantum bits, we can realize this non-Abelian topological order, and it emphasizes how strange these things are. And then you can ask about generalizations. So it turns out this process with measurement can prepare many other kinds of topological order, but not all of them. At least we don't know how to do them for all of them. Gives you some separation of these non-Abelian topological orders. And the place where they separate is really the notion of a solvable group. Okay, so solvable group is in it. I guess the word group itself was introduced by Galois when he was thinking about solving polynomial equations. So these polynomial equations, if you ask, do they have a formula like a radical formula, like we have for the quadratic? The answer is yes, if the symmetric group of that polynomial is a solvable group. Okay, and the first time you get a non-solvable group is for permutation of 5 elements, at least the even permutations of 5 elements, which is related to the fact that the general quintet doesn't have a closed form solution, solution in terms of radicals. Okay, so somehow that aspect of the group turns out to be important. It's solvable, we know how to prepare it. And yeah, it's kind of an interesting connection. And eventually we'd like to go towards topological quantum bits. But for that, what is very important is that we do active error correction on these non-abelian phases, which nobody really knows how to do yet. Okay, what we really know how to do is error correction on abelian, like the toric code phase. Okay, but that's really something that's interesting problem, I think, for the future. Okay, let me end over here.
Thank you, Ashwin. Glad to see you become an experimentalist of sorts.
Sorts, yes.
Questions? So I'll start with one. So the measuring this phase of the making the Borromean ring. So you have to compare the state where you did the ring and where you didn't. So you have to do a control the operation of doing the braiding on or making the ring on the state of some ancilla qubit. And so that took 800 milliseconds for the whole thing. Is that what that time axis said?
Yes. If I put it up there, yes, that is right. That's how long it took. Yes.
So that's a pretty
Very long.
complicated circuit to condition all those operations on
Yes.
another guy, and it
Yes.
still works after 800
Yeah,
milliseconds.
you build it out of these control, whatever, CCZs and
Yeah.
yeah.
Wow. Okay.
And the other one is you don't want to do nothing in the other limb of the interferometer. You want to do something that is similar, but just doesn't have the braiding.
Doesn't braid it.
Yeah.
Yeah. Yeah. Okay.
Probably the question. So basically, although it's kind of about states of matter, but essentially it's not about Hamiltonian, it's about a wave function, right? So
Yes,
you
that's right. Yeah.
right. So you design a sequence of operations that do very exotic set of wave functions.
That's right. So really the target here is the wave function rather than of course, when you do the cooling business,
Yeah.
you get the ground state, but you also get, excited states and all of that for free if you put in a little bit of energy. So that paradigm, you really cannot implement on a quantum computer because, it's very far from equilibrium and all that. But the flip side of it is you have complete control. So you know the state of each of the qubits, so you're able to, control the state of each qubit. And the thing that in the limiting factor is you will get errors, right? If you try to scale this to thermodynamic limit, your operations are not going to be perfect. So that is the analog of the temperature. In the other case, you're going to have errors. It's not exactly analogous, but it's the thing that will mess you up.
It messes up, but I mean, I understand this wave function is so beautiful that I'm not allowed to ask a question about Hamiltonian, but still, I would say the temperature comes in if you have some dynamics, and here, I think it's just inherently there's no dynamics, so just
Yeah, the analog of, like for example, that of course, even when you create a fractional quantum Hall state in the lab, you don't really find the zero temperature state. You always have some density of excitations above it, right? You're at some finite temperature, you excite some particles.
Right.
And the analog of that is that we don't prepare exactly the state that we want using these unitaries and measurement or whatever procedure you want. You will have some errors. Getting rid of those errors, if you want to, maintain that state for a long time, that's where this active error correction comes in.
Right.
Yeah, so I don't know exactly how to answer the question about Hamiltonians. You're right, there's no Hamiltonian. But you can ask the question of cooling, the analog of cooling in the two cases, where you get the state you want, but there has to be something active in this particular case, especially if you're going to do operations on it, in order to keep it, within this phase of matter. And that is where the error correction comes in.
Right. Unlike the quantum hole where basically the interactions
Yeah.
do the job.
Yeah, I mean, there, of course, the whole cryogenic stuff is doing the job for you, keeping it cold, right? And there too, if you're going to, do computation with it, you'll probably have to keep cooling. You can't just stop. So,
Thank you.
Hi. So great talk, thank you. In reality, your measurements are also unreliable, and so in the abelian case, you can get over this by decoding a space-time volume.
yes,
Can you do something similar in the non-abelian case as well?
yes, we think something similar should occur. Work over here as well. Yeah, that if you have like spam errors, you're just reading it wrong. You kind of repeat the measurement and then make sure that you've gotten it right, and then change your mind about what you did after that. But the full theory of this non-abelian error correction has not been worked out. And that would be, I think people have started taking steps in that direction numerically. But questions like, is there a threshold, right? Like we have for the toric code, that's, would be very interesting.
Okay, I don't see any raised hands on Zoom, so let's thank Ashwin again.